Welcome back. In this video, I'm just going to do the solution to the problem I posed at the end of our intro video. This big intimidating integral right here. Okay, so we look at this and we see that it's a rational function, right? Polynomial top and bottom. And it is a proper rational because the degree on top is 3, the degree on the bottom is 4, so we're good to go with partial fractions. All right. So step 1 to executing partial fractions is to factor the denominator. So that's what I'm going to do first. Both these terms could lose an x squared. So I'll take out x squared, and what's left is x squared plus 1, and that's fully factored now. This is an irreducible quadratic. This is a repeated linear term. So I'm going to split this into a over x plus b over x squared. For just the x squared part, right? We've got to count up to that power. And then x squared plus 1 is the last denominator. Because it's a quadratic, it potentially could have a linear numerator. So to leave space for that possibility, we'll say cx plus d. I do want to take the time to point out here that if you put this term first, you'll have like an a and a b here, and then c and a d there. The order doesn't matter at all because the numbers always end up in the right spots, right? So if I get a equals like 5 out of this, but this top for you was c, your c is going to end up 5. So once we actually fill it in its spot in the end, our answers will look identical. So that part, the order isn't really important. Okay, so these are my 3 partial fractions. Step 2 that we said in the last video was multiply both sides of this equation times that common denominator. And this one's going to be trickier than the first example. So if we multiply this side times this denominator, there is cancellation, but it's not as symmetrical as it was before. So over here, this cancels out from that multiplication. My left-hand side is just that numerator polynomial. That's just going to tag along for the next several steps. Okay, so if I imagine this distributing into just the a over x first, a pair of x's top and bottom cancel. So this x is totally gone, but this x squared is only knocked down to regular x. So I have a times one of these x's times the x squared plus 1. Okay. And then if I distribute it into this one, the x squareds perfectly cancel. So now all that's left with the b is the x squared plus 1. And then finally, the cx plus d, x squared plus 1's cancel, so the x squared is left. So I have cx plus d times that x squared. Okay, step 3 in our numbered list from the last video is to distribute everything, essentially clear out all your parentheses. I'm going to keep that left-hand side. I have ax cubed plus ax from this first one, bx squared plus b from the next, and then this one's a little awkward. I'm distributing it in from the right, but it still works. So I get cx cubed plus dx squared. Okay, and then step 4 is collect by powers of x. So I'm going to go in descending order. So the highest power of x I see here is x cubed. This term and this term have an x cubed. So I'm going to put them together as a plus c times x cubed. So the coefficient on x cubed over here is a plus c. Okay, so now these are taken care of, or cross them out, and say, okay, the next power down is x squared. This guy has an x squared, and so does this one. So I'll put them together as b plus d x squared. Okay, so now they're both accounted for. I'll cross them out. The only one with an x, just a plain x, is right here, ax. So that one goes next. And then the only one that has no x's at all is this b right here. So that goes last as like its own thing. Okay, copy down that left-hand side one more time. Okay, so now I'm at the step where we match up all the coefficients, right? So what is on x cubed over here equals what's on x cubed over here, and so on all the way down to the constant term. This is the step where the x's go away. Remember, we're not solving for x over here. We're solving for just those capital letters. Okay, so I know that a plus c, the coefficient on x cubed, has to equal this 2. This b plus d, this is the coefficient on x squared, so it must equal the 4 that's over here. And then this part really makes the solving in the next step fairly smooth. The a and the b are just their own coefficients. There is no x term over here, right? We just go straight from x squared down to the constant. So it's like there's a 0x. So this a must be 0, and we already have one that got solved for. Something similar happens with the b. So the b is the constant term. It's a -1 over here. So right away, we say, oh, well, b must equal that -1. 2 of them are solved for. So I can come back to this one and say, oh, well, I know b is -1. So I'll plug that in, and I can solve for d. D is 5. And then I can come over to the far left one and say, oh, well, I know that a is 0. So c must equal 2. And I have all 4 of my letters. All right, so I'm not done. I'm just done with my partial fractions. So I have a, b, c, and d. I'm going to come back to my original integrand, or integral actually, and just reformat the whole thing and hope that it's more manageable from here. And I'm going to need more space, but I'll come up here just for now. Okay, so I had a over x. A was 0, so this is 0 over x, which we can just, completely disregard in the next step. That's just not really there at all. And then b over x squared. We said that b was -1, so I have -1 over x squared. Okay, and then cx plus d, so that's 2x plus 5 over our irreducible quadratic x squared plus 1. Got some paper to keep working here. Okay, so now I'm going to ignore the partial fractions part and just worry about actually integrating what I have now, because this still is not easy peasy from here. This is going to be more than just one step. Okay, so 2x plus 5 over x squared plus 1 is the problem. As is, it's not something that's doable very quickly, so I'm going to split it into 2 separate problems. So I have -1 times 1 over x squared. This one I'm just reformatting a little bit. Actually, why don't we do 2 things? I'll even take out the 1 over x squared, and we can call that x to the -2. So that one is ready to roll. Whenever I actually integrate, I can just reverse power rule that guy. And then I have 2x over that denominator. Oops, I don't know where that 2 just came from, x squared plus 1, there we go. And then a 5 over the same denominator. So I split up this big proper rational into 2 pieces, and each of these pieces is doable on its own. So I'm going to take another step and split this all up just so it's really clear to our eyes how I'm integrating each. So I have -1 x to the -2. We'll just make that its own integral. I'll have 2x over x squared plus 1 dx here. And then that 5, I'm going to take off the top of x squared plus 1, because this I know is inverse tan or arctan's derivative. So this is one step, this is one step. The one in the middle here is not one step, but as is, it's doable. We can do a u substitution where u equals that denominator. So this whole integral in the middle becomes 1 over u. That's the 1 over x squared plus 1. And then the 2x dx right here is a perfect swap for our du. Okay, so we're ready to go here. Okay, so -1 x to the -2, that -1 carries down. -2 plus 1 is -1. So I have 1 over -1 x to the -1. I'll clean that up in a future step. Over here, this would give me ln of the absolute value of u. I have ln absolute value, and I'm going to put x squared plus 1 back in for u. Okay, and then finally, I have 5 times, I always use the arctan notation, but inverse tan is also fine for something like that. If no one's telling you to simplify, you could leave it here. I'm feeling compelled to cancel these -1s. X to the -1 is 1 over x, so we could format that a little differently. And that is my final answer.